Hello and good morning, dear students. Now we are continuing our next lecture. Next lecture is on differential cross section, impact parameter, and total cross section for scattering. Now, all these differential cross section, impact parameter, and total cross section, all those are related to scattering of very large number of particles. So if you have very large number of identical particles, so why very large number of identical particles? So because single electron, single proton, okay, or single atom, we cannot take into account for scattering, since there are very millions or trillions number of identical particles are involved. So for such case, if you have such case, then such particles are known as identical particles. And if that number is very large, okay, so for that case we have to take into account differential cross section, impact parameter, and total cross section, because we have to talk in terms of probabilities. Why we have to talk in terms of probability? We have to take, suppose we have like 10,000 particles are incident, and we are taking certain angle, suppose zero point 0.1 radian. So out of that 10,000 particles, all the particles are not scattered in that particular direction. So we have to talk in terms of probability. So if you take into account in terms of probability, we have to discuss that into by taking into account a differential cross section. So first of all, we are going to study what is mean by differential cross section. So differential cross section is having dimensions of area. So for that case, if very large number of particles are come into play, and what is that area which is imposed on that particles? So for that, consider beam of particles which is characterized by reduced mass mu and intensity I, okay, of that particles. So in that case, if we can show that by like this, okay, so this is beam of particles which is incident on, we can say, scattering center, which is at O dash. Now here, due to this scattering center, okay, due to this scattering center, all the particles which are coming like this are going to scattered. Now, if that particle came like this and scattered in all direction, okay, some particles are scattered in this direction, some particle are scattered in this direction, some are in this direction, and some particles are scattered in the backward direction. So particles are scattered in the all 4 pi direction. Okay, so here we on the blackboard we cannot show all those directions like this. If you take flow of water which is coming like this, and here you have some obstacle in the way, so you can see that water is flowing in the all directions like this, like this, like this. So in that way, particles are came which in these directions are scattered in all the directions. Now here we have to take two important concept. First one is intensity. So how we define intensity? So intensity of particle is defined as number of particles, okay, which are scattered or coming in this beam per unit area which is perpendicular to this. Suppose that beam is like this, then area you have to take perpendicular to that direction. So if you take that beam in this shape, so area is a circle. So you have to take area of circle. So number of particles which are incident per unit area per unit time. So this is the definition of intensity. If intensity is higher, then we can say number of particles which is coming in this area is very large per unit time. Again, here if you take this mu, which is reduced mass of all these particles, okay, if you take reduced mass mu for all the particles, again next important concept is solid angle. So you already studied what is mean by plane angle. So plane angle is two-dimensional angle. Okay. So like this, you can show this angle is plane angle, which is two-dimensional. Now solid angle is a three-dimensional angle. And for case of scattering, we have to take solid angle because scattering is all in the 4 pi direction. So that's why we have to take 3D angle into calculations. So if you take that angle, three-dimensional angle, so that angle is known as solid angle. So here for taking solid angle, you have to use spherical polar coordinate system. Okay. So in spherical polar coordinate, you already know what is mean by theta, okay, and what is mean by phi. So this is azimuthal angle. Theta is the angle along z axis. So those angles are used to specify solid angles. Okay. So spherical polar theta and phi angles are very important. Now here, if beam of particle having intensity I came like this and scattered from this force center, which is at O dash. So in that case, if you take particular solid angle, suppose I show that solid angle over here, which is d omega dash. Okay. And if you take this angle as theta dash and this as z axis, then you can write dn. So dn is the number of particles which are scattered by angle theta dash in solid angle d omega dash. So that number is directly proportional to intensity. Why? Because more and more particle came, more and more particle will scattered. Since intensity is directly proportional to number of particles, that's why if particles which are scattered in solid angle d omega dash is directly proportional to intensity, and this is also proportional to d omega dash. Okay. So why that is proportional to d omega dash or solid angle? D omega dash is this solid angle, because if you take very large solid angle, so number of particles will increase which are coming into this particular direction. Now you can write this as dn is equal to sigma omega dash, okay, d sigma dash into I, where this is constant of proportionality and this is known as differential cross section. Okay. Now this differential cross section also can be written as derivative of sigma with respect to omega, so d sigma upon d omega. That's why this is also known as differential cross section. Okay. Now from this you can make definition of this. So sigma omega dash is equal to dn divided by I, okay, divided by d omega dash. So what is the definition of differential cross section? Differential cross section is defined as number of particles scattered in solid angle d omega dash per unit incident intensity of the particle. Okay. So I will repeat that definition again. Differential cross section is defined as number of particles scattered in solid angle d omega or given solid angle, which is d omega, per unit intensity of incident particles. So in another words, how we define differential cross section? Suppose 1000 particle are incident in particular direction. So if you take particular solid angle, so how much particles are came in that direction, that we have to talk in terms of probability. Suppose that probability is 50%, we can say out of 1000 around 500 particles are came in that direction. Here I is the total number of particles. Recall how we calculate probability. So if you toss a coin, so there are two possibilities, either it is head or tail. So intensity, why we are taking intensity? Because all the particles came in that direction. So out of all those particles, how many particles are scattered along given solid direction, along given solid angle direction? So this is nothing but probability. Now this is having dimension of area. Okay, this solid angle. Now if you take sigma omega dash d omega dash term, okay, now d omega dash is the solid angle, which is, I told you earlier, this angle can be represented by spherical polar coordinate system. So how we that represent? So that is nothing but sine theta dash d theta dash d phi dash. Okay, so this is the element, volume element. If you multiply with r square, so that is volume element. You are taking only angular part of spherical polar coordinate system. So d omega dash is sine theta dash d theta dash d phi dash. So if you take this sigma omega dash d omega dash, now this is equal to, here sigma is function of omega dash. Now here we replace that omega dash by theta and phi. So instead of d phi dash, if you take d phi, okay, as a total angle, so that is 2 pi, okay, sine theta dash d theta dash into sigma, which is now function of theta dash. Here sigma here is function of theta, omega dash, here this is function of theta dash. So you can write this term as this. Okay. Now we are using this for studying impact parameter. Now with differential cross section, we are moving our next section to impact parameter. Again, for impact parameter, we have to take beam of particle. Okay, now that beam of particle is having intensity I. If you take cross section to this beam of particle, now this beam of particle is having cylindrical shape, then you can take cross section as circular. Suppose here we have that force center, which is at O dash. This is Z axis. Now all the particles are coming like this and going to scatter. Now as I told you, all those particles are scattered in all the 4 pi direction. Okay, so like I told you example of flow of water. So water is coming like this and there is some obstacle. So water is coming like this, all the 4 pi direction. Some is going like this, some is moving towards, some is moving forward. Now from here, if you take again the particles which are coming like this, so this particle will go like this particle will go like this. Okay, now this is the angle theta dash and this. So S is the impact parameter. Okay, so if you take this circle which is having thickness ds, okay, So this distance is s, and this is having thickness ds. So what is the definition of impact parameter? So impact parameter is the perpendicular distance. See, this is the perpendicular distance from the force center, perpendicular distance to the direction of velocity. Now, after impact parameter distance, the particles which are scattered from force center, uh, the scattering, we can say scattering is less compared to that. See, if particle from here, which is very large distance from impact parameter, will came, so particle will go like this, so they are not scattered. So scattering is more for the distance up to impact parameter. So impact parameter decides the degree by how much those particles are going to scattered. Okay. Now, if S is the impact parameter, which is perpendicular distance from the force center to the direction of velocity of those particles. If you take particles which are coming from this circular annular disk, okay, so dn is number of particles, okay, per unit time coming towards O. So how we can find out that number of particles? We know that intensity is what? Number of particles per unit area per unit time. So number of particles per unit area, number of particles per unit time is nothing but intensity multiplied by area. So that number dn, okay, so dn is equal to now intensity I multiplied by area. Now area of this annular ring is 2 pi s multiplied by ds. So 2 pi is circumference and multiplied by ds. ds is the thickness. So call this as equation 1. Now from previous section, here you can write dn is equal to now that number. Now this number is the number of particles scattered in given solid angle d omega dash. So dn is equal to now we can write I, okay, into sigma omega dash into d omega dash. But you can write sigma omega dash d omega dash in terms of theta, okay, because here you have to use notation theta, as this is equal to I into 2 pi, okay, sine theta dash sigma theta dash d theta dash. So call that as equation 2. Since this is the number of particles which is coming from this annular disk, and this is the number of particles which are came, so this particle came like this and scattered. Okay, so both the particles having are same. This is number of particles coming, okay, this is number of particles scattered, okay, through this annular disk. So we can equate equation 1 and 2. So then you will get I into 2 pi s ds is equal to, on the right hand side, dn is nothing but I into 2 pi sine theta dash sigma theta dash d theta dash. So this I into 2 pi will cancel, okay, and you will get equation as s ds is equal to sine theta dash sigma theta dash d theta dash, or sigma theta dash is equal to, you can take this term on the left hand side, so s divided by sine theta dash ds divided by d theta dash. Now ds is what increment in s, and d theta is what increment in this angle. As s goes on increasing, means we are moving up and up, So this theta dash which is scattering, so that angle is decreasing. As s goes on increasing, this theta dash angle goes on decreasing. See, as we move away from this force center, the scattering is less. Okay, as I told you earlier, that's why we have to take this term as mod of ds by d theta dash, because this term is negative. This is what differentiation of s with respect to theta dash. So this is again another relation of differential cross section. So sigma theta dash is equal to s divided by sine theta dash divided by ds upon d theta dash. So differential cross section is in terms of impact parameter, we can use this equation and we get another definition. So this is an effective area. Okay, so effective area posed by the scatterer, posed by scattering center, okay, to particles. So differential cross section is nothing but effective area which is posed by scattering center to the particles. Now total cross section. So as I told you, differential cross section is nothing but is for this differential cross section is for only particular angle d theta dash. Okay, if you take total angle or total number of particles, so that's why we have to take total cross section. So total cross section you can write that as sigma t, which is theta, is nothing but integration over sigma theta dash. Okay, d theta dash. So total cross section is this. Now from definition of this you can write this is equal to total cross section, okay, which is function of theta dash is integration s divided by sine theta dash, okay, ds divided by d theta dash into d theta dash. Okay, so this integral you have to integrate over theta dash, which is running from 0 to pi. Now total cross section is defined as number whole all the number of particles which are scattered in given all the solid angle. Okay, so with this we finish this topic, which is differential cross section, impact parameter and total cross section.